Okay, welcome to your video lecture for section 10.3 on the Fourier convergence. In the previous lecture we showed that if we have the Fourier series converging to a function f, then the coefficients are given by these inner products of f with the Fourier basis functions. Okay. It also follows that because the Fourier basis functions are 2L periodic, that f will have to be 2L periodic. In this section we'll go in the other direction. We'll assume that f is given, and we'll try to determine which kind of properties f needs in order to have a convergent Fourier series. Okay, so what we'll find out here is that if f is periodic with period 2L, integrable on the interval negative L to L, then the set of coefficients can be computed using the formulas derived in the previous lecture. The main question is whether or not this series converges, right? So you can write down a series, but you don't necessarily know it'll converge to something meaningful. And if it converges to something meaningful, does it converge to the function f at each x? We saw in the last lecture that at points of discontinuity, the series, because it's continuous, had a difficult time converging to a point because f was a different point on either side of the discontinuity. And so what we'll have to do here is we'll have to put restrictions on f. So specifically what we'll assume is that f and its first derivative are piecewise continuous. You remember what that's from the Laplace transform section. And the function's 2L periodic. If these conditions are met, again, that f and f prime are piecewise continuous on the half-open interval negative L to L, and the function is periodic with period 2L, then f has this Fourier series with the coefficients given in the last lecture. The Fourier series converges to f of x at all points where f is continuous. So when f is continuous, the Fourier series converges to that function value, f of x. And when it's not continuous, what it does is it converges to this average of the values of f around a point of discontinuity. So f of x plus is the right-hand limit of the function at x, and f of x minus is the left-hand limit of the function at x. And we add them up, we divide by 2, that gives us the average, and that's where the Fourier series will converge to at points where f is discontinuous. Okay, so for our example, we have f, which is negative 1 for x greater than or equal to negative 2 and less than 0, and 1 where x is greater than or equal to 0 and less than 2, with the supposition that f is 4 periodic. We know that f and f prime are piecewise continuous. It's a constant function at all but countably many points. And thus, by the Fourier convergence theorem, we know that our Fourier series that we computed in the last lecture will converge to f everywhere but at the points of discontinuity, which just happen to be these even integers. And at those even integers, it converges to 0, which is the average of the function at those discontinuity points, right? So the average of negative 1 and 1 is 0. And so we have a look here, again, at the same figure that we had in the last lecture. Let's look more at the case where n is 16 because we're getting close to convergence there. Notice at the points of discontinuity, we see that the function value approaches that average value, 0. And then everywhere where it's continuous, we have the series converging to the function values there, just as the theorem suggests. Okay, thank you.